in and she was trying to, like, I don't know, draw blood or whatever she was trying to do, and the patient was like so aggressive that she got like the needle punctured her. And she said like her first thought was this patient could be like, you know, an HIV patient. So they have to like conduct the test, like, and early enough they did the test and she was right, like her instincts were right. The patient was actually an HIV patient, and she was freaking out. And she has to like go through all these procedures, and she was on medication for like a month, and yeah, it wasn't really that great. And I thought this story was like really similar.
Yeah, that's really fascinating.
It's like,
So, you know, you guys are aware of the case studies that each of the chapters has. And how ironic is that, that this is not just a story the author made up. This happens every day.
yeah.
And I know you guys in nursing probably talk about needle sticks, I would hope, and how you can kind of try to reduce the likelihood of that. But if you get a patient who is on medication, you know, on drugs, you know, there's lots of reasons why people can be very belligerent and put up a fight. Yeah, wow, that's scary. That's one of those things that I think going into healthcare, and we of course have been appreciative of all of the folks in the front lines with COVID now, putting their lives on the line, really, right? Um, Boy, that's another sacrifice that I don't think many people understand. So thanks for sharing that. That's really interesting. So welcome everybody. It is Thursday the 23rd. I've started to record this, and Emily reminded me that I had not posted the recordings from the 21st. And so that is being uploaded as we speak. And I'm sorry, I always try to religiously get that done right afterwards. But for whatever reason, I can't recall what Tuesday was like. It was a crazy day. They all seem to be sometimes. I didn't get it uploaded. I saved it, but I didn't upload it. So please ask me, tell me if something's not visible or accessible for you guys. So we'll just start like we always have, and that is to open it up for questions related to lab. I'm not sure if we have any of the lab folks here today or not. Corey was here Tuesday, and Jerry and Rebecca, I don't know that I've seen her much at these meetings. So any questions on lab stuff? We were looking at, grab my lab syllabus. We were looking at the Kirby Bauer stuff, and disinfectants, antiseptic effects on growth, and hand washing. Any questions on those exercises? You've got a few videos, I think, in the course shell to look at. All right. Then let's open the floor for questions related to chapter 13 or 12 or 11 or 10 or 9, whatever suits your fancy.
What's the difference between selective toxicity and narrow spectrum? I'm having trouble like trying to differentiate the two.
Selective toxicity. Where in chapter 12 did they specifically say that?
I think it's like really towards the beginning, like the first few slides.
Oh, okay. So let's pull that up.
So isn't there selective and then narrow and broad? Is that what you're talking about?
I think so. Okay, so do you guys see the chapter 12 PowerPoint?
No.
No, okay, all right. Okay, hang on. Now, still not?
Mm-mm.
No.
No.
Okay. Okay, I'm gonna stop the share and I'm gonna try it again. How about now?
Yeah.
Yeah.
Okay, so Maggie, I think it's probably somewhere in this section of chapter 12. You said it was early in the PowerPoint,
Yeah.
and this is one of the first ones. So where, just,
I think it's the next slide.
Selectively toxic is 13.
okay, thank you. Okay, I think one could probably use that term selectively toxic for either a broad and or narrow spectrum, in the
Okay.
sense that this is just a more generic description of how, you know, some of these drugs that are targeting, for example, prokaryotic ribosomal units would not necessarily be too concerning or worrying to you and I because we don't have those, while other antimicrobials that say are targeting cell membrane, antifungals come to mind, we might need to be a little more cognizant of because we also have plasma membranes. So I think that's basically what that's kind of talking about.
Okay.
Does that make sense?
Yeah. Yeah, there's just in one of the slides that are like crossed out, there's a question like
Oh,
pick what one it would be.
okay. Yeah. I'm just looking for that. Oh, it's probably this one here, huh?
Yeah.
Oh, I see what you're saying. Yeah. Right. That's probably why I didn't include those two in the PowerPoint. So that's not something you need to worry about in that sense.
Okay.
Okay, other questions on 12, or like I said, it could be any chapter you want to talk about. So you're going through these and, you know, you're making notes to yourself as to what is making sense, what isn't. I mean, that's what you should be doing, right? Is this somewhat easy to go through? It's just a function of there's so much material, you know, you have to digest. That's the real, I don't say problem, but it's a function of amount of information. Yeah.
Sorry, is all of chapter 13 going to be on the exam?
No, I think we said that none of chapter 13 was going to be on the exam.
Oh, that's nice. I had no idea.
Because I told you in one of the meetings that I never thought it was very fair in any of my classes to have a chapter covered early in the week and then expect a student to be tested on it later in the week. I don't think that's fair. That's just my opinion. Unless there's some overriding reason why we might want to put a part of the chapter on it. But no, I mean, you know, you've got enough chapters, right? You've got part of 9, 10, 11, and 12.
Yeah. Okay. I missed one Zoom meeting, so I'm assuming that's when you talked about chapter 13.
Does everybody agree with that?
Yes.
Mm-hmm.
Yeah.
I don't think I said we were going to put 13 on.
Yeah, no, you said that 13 wasn't going to be on there.
Yeah, because it's just, I don't think it's fair to. give you such little time. And again, I'm just going by the syllabus, obviously, as a rough frame of reference here.
Can you go over the, like for the therapeutic index, or like the measuring antibiotic effectiveness, the therapeutic index? It's like the very last
Yes.
couple of slides.
Okay, so let's see, this is down. Okay. Trying to put you guys somewhere where you're not blocking the screen. Okay. Are you guys seeing me move you around here?
No.
No, you're just seeing the PowerPoint screen where it says comparing mix?
Yeah.
Okay, great. So it's just me seeing you guys, all right. So this minimum inhibitory concentration, are we good with that concept? We said this was the minimum concentration needed to kill the bacteria, and we could assess that in a number of different ways, one of which would be to utilize these e-test diffusion strips, which I've never used, but I would love to try them because I think they're really interesting. Do you remember what these were? Okay, that's pretty easy concept to understand, right? And then this is just an alternative way of developing that same information, and that is a more laborious setup whereby we're doing broths, we're inoculating all those broths into a prescribed dosage of drug, and we're looking to see what's the MIC, which of course is going to be the 1.6, that lowest dosage, which results in no growth, as evidenced by the clearing of the, of the turbidity, no turbidity. Well, we have growth in all these other guys. All right, so this therapeutic index is a mathematical number. And we didn't spend much time on this, but there are labs that I remember having taken where we do come up with a therapeutic index for a given drug or antibiotic. So as it mentions here in the slide, you take the dosage that's toxic and divide that by the MIC, basically. And so every drug that you might be prescribed, you could go to a document whose name I cannot tell you, but there's some document out there that physicians have access to or researchers have access to that would list the therapeutic indexes for all of the drugs. And there may be times, let's say, for example, when a given antibiotic is insufficient to control the infection. So we may need to balance this with the utilization of maybe a drug with a lower therapeutic index. In other words, increased toxicity to the human, potentially, but the benefits of using that drug outweigh the disadvantages of the patient, say, dying if we don't give it to them. So there's a lot of factors that go into the determination of when you might use a given drug. It could be the patient's health. It could be the fact that we don't have any drugs that we've done a lot of research on yet. And that's, of course, the case with COVID right now, right? We don't have a lot of data, baseline data for all these different potential drugs. By the way, not to go off on a tangent, but did you hear recently about the chloroquine test results on COVID-19 people?
They don't seem to be working.
Not only does it not seem to be working, but there's a higher mortality rate for patients who have been given that versus those that haven't. Did you hear this in the news this week? Yeah.
I saw something about that.
Yeah. And that's why people were on Trump's case for not publicly saying anything until we have the data. Because here we go, we've got the data, and the data does not support them to support it as being a viable drug to use. Again, I'm not trying to be political here, but how can you not be in that particular instance? You've got to be very careful and cautious when you make public statements. So a lot of drug trials are being done as we speak, looking at that fine balancing act between being effective as a drug against a virus or bacterium or protozoan or whatever it might be, and the potential toxic impacts. So that's basically what I'd like you to know for the therapeutic index, not much more than that. It's a value, a number calculated based upon toxicity and minimum inhibitory concentration dosages. Other questions? Come on, you guys should have questions. Things you want to review.
Can you review like the types of resistance, like the pumps and thicker walls and
Sure.
all of those?
This is
That whole
really,
picture?
yeah, because this is a perfect essay question, isn't it? Think about it.
That's why I want you to go over it.
Yeah, there you go. Discuss 3 of the 5 mechanisms of drug resistance. I mean, it's a perfect essay question. And this is, I think, just super interesting. The ways in which bacteria have, through evolution, developed systems to get around the effects of toxic productions by their close cousins. I got to think about this in the context of out in the real world, not necessarily in our world, although this happens as a result of use of drugs too. When we give drugs to bacteria to control them, they try to get around it, in the same way. But these mechanisms that we're looking at here, this hasn't just started up in the last 20 years. This has been going on for 3.5 billion years, right? How long have prokaryotes been on Earth?
Billions.
Yeah, 3.5 billion years or more. Yeah. So this is a process that has been going on for a hell of a long time. Have we hastened or sped it up by using more and more drugs in medicine, trying to control bacterial infections or viral infections? Yes, certainly we have sped up resistance, but understand that this has been going on for eons. Okay, so you guys see the first one listed on the screen there? Yes?
Yes.
Yep.
Okay. Just want to make sure that you see it. So this first one is specifically, of course, talking about penicillinase, which is a what?
Protein.
Enzyme.
It's a protein, but specifically, what kind of protein?
An enzyme.
An enzyme, right. And we know that because it ends in ASE. So this should look somewhat familiar to you. And by that, what am I trying to say? I'm trying to say that if you look at the chemistry of that molecule, not that I'm expecting you to regurgitate it or write it on a test, okay? That's not what I'm saying. But you should be able to recognize this as this ring here as a what?
Beta-lactam.
Right, and this one? Doesn't this guy have a name too? I'm thinking about that slide that I put up here in one of these PowerPoints. Well, anyway, the beta-lactam ring is the square one, as Maggie said. There's a name for this guy too, and I just can't think of it. Okay. And so when we introduce the penicillinase, as another bacterium might try to do, in response to the antibiotic being secreted by its next door neighbor trying to kill it, it deactivates the penicillin. It breaks, of course, the bond here between this nitrogen and this carbon, which is in the corner, right? So if you break this bond, just literally breaking the bond is all it takes to render this antibiotic inactive. Now remember, penicillin and its derivatives are basically there to prevent peptidoglycan formation, right? Cell wall production. So that's one very specific example of how an enzyme can, in essence, deactivate the antibiotic by affecting its chemistry. And I'm sure there are others too. The second one is talking about how many drugs, in order to affect a cause or change the microbe, try to kill it in some way, has to be able to get into the cell. So this is the microorganism. Obviously, we're looking at the cell membrane. They say cell surface, but think of it as a cell membrane perhaps. And these receptors that you see here are proteins, oftentimes. And so if the drug can fit into the receptor site, it is allowed in, and then it somehow kills the cell. And of course, here we're talking about basically taking that normal protein conformation or three-dimensional structure and altering it such that it is irrecognizable, if that's a word, to the drug. In other words, the drug can't fit into the protein and be allowed in. And in order to kill the cell, it's got to get in. Well, it can't get in, the cell's not going to be harmed. So you're basically altering the conformation of the surface protein of the microbe, which the drug ordinarily would use to gain entry. This is fascinating, called efflux. Okay, so let's say the drug gets in. We don't alter the membrane protein. Well, okay, well, maybe if we can at least prevent that drug from working by pumping it back out as quick as it comes in, that's going to be fine for the cell here. It's not going to die from the drug. So this efflux process is involving the evolution of pumps. Now, if you think back to A&P, has anybody ever heard of sodium-potassium pumps?
Yeah.
Yeah. Okay, where one end of the molecule, one end of the protein pumps the calcium or the potassium in, and the other one pumps it out. This is important with respect to maintaining a resting potential, let's say, of a neuron or something like that. It's the same basic idea in the sense that we have here a protein pump that is specific to this molecule in terms of pumping it in one direction, and that is out of the cell. So yeah, it can come in, but just as quickly as it comes in, it gets pumped out. And I think, if I remember right, if you click on efflux, if you're in the PowerPoint slide, it takes you to a video, I think. This particular next mechanism actually could be expanded to not just one, but actually 5 different ribosome impacts. If you look on page 368 of the textbook, figure 12.5, there it talks about major antibiotics and their actions on inhibiting prokaryotic ribosomes. Okay, so this is just one example of a drug, as illustrated here by the green triangles, basically preventing any sort of translation of the protein. Again, I'm assuming you know what translation is. So we have the 2 subunits. We have the messenger RNA here in yellow, These funny looking orange guys are transfer RNA, which you know brings in an individual amino acids, although this last guy is really carrying or containing the long elongated polypeptide. This guy just brings in the next one to be added, right? So if this drug gets in and somehow causes the large and small subunits to dissociate and break apart, well, there goes messenger RNA. You need that, don't you, for the transfers to come in, because its anticodons must meet the codon and not meet, but kind of bond complementary to the codons here of the messenger RNA. You're not going to have normal protein production, are you? Because the drug is impeding the action of the ribosome. But again, this is one of many different ways in which drugs can target ribosomes. So again, 368, check that out. And this fifth example is simply kind of going around the action of a drug. So let's pretend we have a particular drug that somehow prevents the conversion of substrate B into C, which ordinarily would then be converted into D and some end product that the cell needs. Well, the drug ordinarily would prevent the synthesis of the desired end product. In other words, the bacterial cell that's trying to be killed can't make the proper product because the drug prevents this very important enzymatic reaction, let's say. So what does the cell do? Well, it circumvents the drug's action. It says, okay, if you won't let me make C, then I'll make C sub 1 from B. And I'll make a D sub 1, and then I'll make the product. Either way, I'm going to make what I need to make. You're not going to prevent me. I'm just going to go around you. So that's kind of cool. It's just going around the problem, so to speak. Choosing an alternate pathway, metabolic pathway, creating, in essence, a new pathway. So that's kind of interesting. Do you remember us talking in one of these, well, actually was page 369, talked about the conversion of PABA into folic acid and the two antibiotics that tried to target the formation of folic acid? Remember the sulfonamides and trimethoprim? We talked about that on Tuesday. Well, that's a classic example of how some cells may try to get around the action of sulfonamide or trimethoprim by choosing an alternate metabolic pathway. I'm sure that process, that evolutionary process, you know, may be at work as we speak. And the day may come when sulfonamides and or trimethoprim may not be effective in preventing folic acid production and then subsequent, you know, TA, CG, and amino acids being made by the cell. So does that answer your question, Emily? Emily still here? Yep. You didn't get booted off yet. Good.
Yes, that answered my question.
Good, good. Okay, how about other questions?
I have a question, but like I don't know if this is happening to anybody else because like I can't get some like I have on my phone, I can't get most of the links on PowerPoint 9. Like in the PowerPoint 9, there's like a lot of like it says like hyperlinks and stuff like that, but like if I won't do anything. And there's like a 10-minute link on like Joseph Lister, and I can't get that to work either. Like some of the videos that you have like in the PowerPoints, I can't get to work.
Has anybody else had issues going to any of those hyperlinks?
Yeah, I can't get to any of them either.
Can anybody get to any of the hyperlinks?
I don't think I can get to some.
Not on the PDF works fine, but the other chapter 9 link doesn't work. I can't get to it either.
You can't open the regular PowerPoint.
Yep, can't open it on a computer. I couldn't open the other one, the regular one. The PDF I could though.
Okay, so that's why in response to Diane, I think, I posted, in addition to the so-called regular PowerPoints, PDF versions of the same chapters.
Yep.
So Olivia, have you looked at those at all, the PDF versions?
No, but I can open up the regular ones perfectly fine on my laptop though.
But you can't get to the hyperlinks.
I can get to some of them, but not all of them. Like last night I watched like 3 of them, but I couldn't get like the other ones.
And Lamont, you said when you did the PDF file, you were able to get into those videos?
Yeah, with the PDF, I was fine.
So Olivia, I would say try the PDF versions.
Because there was like a certain slide that I knew like I couldn't get. I think it said like 86 or something. Yeah.
But you haven't tried the PDF for that.
Because the other ones have worked perfectly fine. Like all the other previous chapters, I've gotten all of the the hyperlinks and all that, and like the regular form. Like I've just watched them all perfectly fine.
Yeah, I would suggest trying the PDF and seeing if you can get in that way.
Okay.
I don't know why some people have issues with the regular PowerPoint version, and maybe I'm just not loading them properly. I've been talking to the IT folks for several years trying to get this issue resolved. It just seems like going to PDF has been helpful. Other questions?
What's the format going to be like? Like our typical test with multiple choice, true, false?
Yeah.
Open-ended.
There'll be multiple choice. Could be true, false. Could be short answer. Could be essay. Those would be the 4 major styles or types of questions. We don't do matching. So yeah, it's very, very similar format to the previous 2.
Will we have the whole 2 hours to take it from 4 to 6, or is it going to be like you have from 4 to 6, but you have an hour and 15 minutes to take the test?
I think I gave you 90 minutes
Okay.
for the test. Yeah. So you have that 2-hour window within which to take it. So, but yeah, you'll have 90 minutes.
Okay.
Any questions? Well,
Sometimes,
go ahead.
like the cell wall and the cell membrane, I get those 2 mixed up all the time. And I'm looking at chapter 12 on slide 12.
Okay. Chapter 12, slide 12. Do you see the PowerPoint slides here?
Yep.
We talked about this earlier. Is this the slide you're talking about?
Yeah. And it's down like more towards the bottom where it says the penicillins are effective in blocking the synthesis of the cell wall in bacteria
Yeah,
and do not harm human cells.
right. Because you have to understand, human cells don't have cell walls.
We have a membrane.
That's a different thing. Yeah,
Okay, I just want to make sure I was thinking correctly on that.
yeah. You have each of your cells, the outer skin, if you will, quote unquote, of your cells is a cell membrane. That's what holds everything in. And that's made up of the phospholipid bilayer with embedded proteins, right? And there's also glycolipids and glycoproteins sticking out. So
Okay. I just want to make sure I had that straight.
yeah. But you have to understand, that bacteria also have cell membranes as well. And so this was covered back in what chapter was it? 4? No, yeah, 4. So go back into chapter 4, and you'll see there somewhere around page 99, they talk about the cell membranes of gram-positive and gram-negative cell wall, or within the outer cell structure of gram-positive and gram-negative cells. 101, if you want to flip to page 101 real quick. So we would put the cell membranes in the category of cell envelope, but the cell wall is typically external to the cell membrane. So when we say cell wall, we're thinking peptidoglycan, right? A thick peptidoglycan if it's a gram-positive cell. If it's a gram-negative cell, then we're talking about a thinner peptidoglycan layer beyond the cell membrane or plasma membrane. And then, of course, we have this outer membrane, which is unique to gram-negative cell walls. But it looks like a cell membrane. It's phospholipid bilayer with embedded proteins, but specialized proteins. Are you looking at page 101?
Yes, I am.
Yeah. So again, at the bottom of both of those cells, closest to the cytoplasm, is cell membrane. They call it plasma membrane. It's the same thing. Plasma membrane, cell membrane, same thing. So you have very similar anatomy to your cell membranes, phospholipid bilayer embedded proteins. But beyond that, bacterial envelopes are unique. We don't have anything like peptidoglycan. We don't have a periplasmic space between the cell membrane and the cell wall, et cetera, et cetera.
Okay. Thank you.
Yeah, sure. So to understand how certain drugs work, especially antibiotics, you've got to understand A, what is the antibiotic targeting? And B, is that target unique to bacteria, or is it common to both eukaryotic and prokaryotic cells? If it's the former, then we don't have to worry about it. If it's the latter, we need to be cognizant of it, because we could potentially be harmed by that drug. If it hurts bacterial cell membranes, it could hurt ours, theoretically, because we share similar chemistry in that sense.
Okay.
That's basically the takeaway from that slide. Kind of getting back to what Maggie was asking. And and that's why we spend some time describing the unique differences between prokaryotes and eukaryotes that we did back in one of the early chapters, right? Prokaryotes evolved well before eukaryotes. They're very different in terms of their cell biology. And we have been able to capitalize on that in terms of making drugs, synthetic drugs, that target just prokaryotic cell biology. Although this is also a natural evolutionary process, natural selection occurs out in your backyard between bacteria as well. Other questions? Can anybody tell me where this photograph was taken that I'm sitting in front of? No?
Was it the South Korean border?
Who said that?
Skylar.
How did you know that? Well, you should know that.
I've seen it before.
You're a military person.
No, I'm not actually.
Aren't you?
No.
I thought your family or your husband or you were, what was that? Somebody in micro was stationed in Alaska. I guess it was last.
No, I've been to Alaska, but I've never.
Oh, that's what it was.
Yeah.
Okay. This is at the South Korea, North Korea border. Yes. This is North Korea, this big building in the back. And the front buildings, the blue ones, are UN buildings. I was there when I was in college.
Wow.
And I actually legally stepped into North Korea under UN guard. I can safely say I was in North Korea by like 2 feet. This is where they signed the armistice back in like 1953. Because, you know, technically North Korea and South Korea, or actually North Korea and the UN are still at war. Do you know that? Technically we are. We signed a sort of a peace treaty, but that doesn't mean peace was declared. So technically still at war.
And I heard like Americans are not allowed into like North Korea. Like Americans cannot go there.
Oh yeah, I mean, it's such a closed society, and maybe you've heard in the news recently that the president, whose name I cannot think of, Kim Jong-un, is they suspect he may be in his health might not be the greatest. Have you seen this in the news the last week? Yeah.
Yeah.
The famous picture of Trump and Kim Jong-un meeting and shaking hands last summer was right here, to my right. Right here, literally right where my finger's pointing. They both crossed and met right there. So it's kind of interesting to be there. The other thing that I'll just leave you with, which is kind of interesting, when we went on this tour, we were told we were briefed by the it was either the UN forces or the American forces, not to make any hand gestures. Because in Korean, if you wave to somebody, which of course to you and I would be a greeting, right?
Yeah.
Korean, that can mean an invitation. Come over and talk to me. So if you're waving to them and they're up here taking pictures of you, and there's photographers taking propaganda pictures all over the place, or at least there was at that time. They could use that photograph of Americans waving to North Koreans as an invitation for the North to invade the South. Now I know that sounds bizarre, but that's the reality of how certain cultures will use that to their advantage. So it was very, very cool, very interesting. Interesting place to visit. Anyway, see what you learn in this course. It's just amazing. Anything you'd like to review? Questions on anything? If not, I guess we will meet then next week on Tuesday, where we will start chapter 14, which is our second last chapter. Questions, comments, complaints? Anything you want to talk about? Okay, then I will see you next week.
All right.
Thank you.
Okay, guys, have a good
Thank you.
weekend.
Thank you.
You bet.
Thank you.
Yep. Bye.